Thank you, Jerry, and once again, thank you, NewEra Software, for sponsoring the zExchange and these crypto sessions. It's hard to believe that this is the 12th, the December session of the year-long focus on crypto that we've been doing, and I'm grateful to New Era for providing that opportunity. Today, we're going to try and kind of wrap things up for the year, and to some extent, we're almost doing two different sessions here, although the second part will be fairly brief. I want to kind of review some of the other technologies and facilities that can leverage the crypto infrastructure that you've got running on System Z. Now, earlier in the year, we did a session on database encryption, and we did one on System SSL, and those are two very important products or technologies that will use the infrastructure. But there are multiple other technologies as well, whether they be separate products or subsystems or whatever. And if you're maybe looking for a solution, maybe this will trigger some things and give you an idea of options that you have available. And maybe you're already running some of these and didn't even realize that it could leverage the crypto infrastructure and the impact it might be having on your environment. So we'll cover those. And then at the end, I want to talk about four things that I think you ought to be doing today to be prepared for the future, whether they're going to provide better security or help you do capacity planning. Just four things that you ought to consider with the beginning of a new year. It's a good time for resolutions, and maybe these are some resolutions that you ought to make for 2015. So with that, let's go to slide 2. So basically we're going to do two sessions today. One on crypto consumers and stuff that we haven't talked about before. We did full-length sessions on system SSL and database encryption and how those two facilities can leverage the crypto infrastructure available on ZOS. There's a bunch of other either products or facilities or things that are available that either can take advantage of the crypto technology, or you may not even realize it, may be able to use that technology when you're doing other things. So I want to cover those kind of quickly. I think at most I've got like 4 slides on some of these, some of the topics even less. But just be aware that the facilities are out there, and if you need the ability to encrypt files for a partner, then you might want to look at something like the encryption facility. So we'll get into those. And then the other session within a session, there's going to be four things that are, I think, important to be doing now so you can be prepared for the future, whether it has to do with capacity planning and performance or just security in general. And if heaven forbid there would be a breach, uh, if you can stand up and say, hey, we've been doing some things to protect ourselves, those that can be very powerful and can get you out of a bind. So let's jump into the crypto consumers and specifically the encryption facility on slide 3. So the encryption facility was actually available on the tools page. You could get this for free at one point, and it's basically just a copy utility. It'll copy and encrypt the file. And what happened was, 10 years or so ago, when tapes were falling off trucks on the way to Iron Mountain, people were screaming that the tapes weren't protected, and customers were looking for a quick and easy way to start encrypting those tapes before they left their environment and got put on a truck to go to an Iron Mountain. So IBM took this tool that was available on the TechDocs website and turned it into a product with formal support, and you have to purchase it. It is a price product. And that original implementation did something that was called Z format encryption, and basically the utility is just an IEB general on steroids. It will take a file and copy and encrypt that file. and then it will stick a header on the front of it with some control information about how the file was encrypted. So you could encrypt the data set, put it on the tape, send it to Iron Mountain. If it fell off the tape, the data was encrypted, and whoever found the tape couldn't read it. But if you needed to bring the tape back in and restore it, recover a data set off of it, you could bring it back. You could use that header information to glean some information about the original file, and then decrypt and recover the original file. We'll get into how it works in a minute, but basically that was what zFormat did. It's just encrypting and putting a header on it. Now, if you had so for backup tapes, there was a feature called the DFSMS DSS encryption feature, and basically that just added similar support to DFSMS DSS, so that when you took a dump, whether it was a logical or a physical dump of the volume, you could put some parameters on the DFSMS DSS control statement that said encrypt the tape or encrypt the data as you created it, and it would do that. And it works similarly in that there was some control information that was captured along and put into the control information for the dump so you could recover it. In addition, if you needed to send a file to a partner, there was the capability to do that. So you could create this zFormat data set, and your partner could read that data set if they had the IBM encryption facility installed, or if they didn't, there were also some utilities. There was the decryption client for ZOS and the Java client. The decryption client for ZOS was intended for your partners that might be running ZOS but did not have an encryption facility license. They could download this decryption client and they could decrypt the files that you sent to them. This client was smart enough to know, okay, here's the layout of the header record, and he could recover the data. If your partner was not running ZOS, or maybe they weren't licensed for the encryption facility, and they maybe weren't running ZOS, or even if they were, they could implement this Java client, which could do the same thing. You could encrypt data, send it to them. They could use this utility on the Java client. In addition, with the Java client, they could encrypt data and send it back to you. Again, the license agreement that you had to sign said that one party, either the sender or the receiver, was legally licensed to the encryption facility for ZOS. As long as that was true, the other partner could use the Java client to either encrypt or decrypt data. Now, in a later version, in version 1.2 of the encryption facility, IBM implemented OpenPGP support. Now, OpenPGP is an open standard. It's Internet Standard RFC 4880 now. The original was RFC 2440. But it describes a procedure, a process for sharing data using what's called the OpenPGP protocol. One of the advantages of implementing the OpenPGP support was that it was ZAP eligible. So if you had ZAPs installed, you could offload the work to the ZAPs and save some CPU cycles. The OpenPGP format can either use X.509 or OpenPGP certificates, and we'll get into a little bit more about that in the next couple slides. So with that, let's go to slide 4. So there's a couple different ways that the product works. For zFormat, you can either use the passphrase option or the RSA option. With the passphrase option, when you perform the encryption, you provide a passphrase, whatever you'd like, Winnie the Pooh and Tigger 2. The encryption facility will take that passphrase, run it through a hashing algorithm, generate a hash that represents that passphrase, and use that hash to be the symmetric key that actually encrypts the data. So if you use the passphrase when you want to decrypt that data, or when your partner wants to decrypt that data, they're going to need that exact same passphrase to be available. They'll run it through the same hash algorithm, and it's the process for recovering or creating a key from the passphrase is documented by PKCS number 12, but they'll need that passphrase to recover the data. Alternatively, you can use what was called the RSA option. And with the RSA option, the encryption facility would simply generate a random number that would be the key to encrypt the data. And the data would get encrypted using that key and written to the file. But in addition, the encryption facility will take that key and encrypt it using a public-private key pair, specifically the private key. So, I'm sorry, the public key. So you would encrypt the data with that public key and store that key, that enciphered key, in that header record at the beginning of the file. When it comes time to read that file, the ciphertext of the key will be pulled out of the header. It will be decrypted using the private key that's associated with the public-private key, and now it will have the actual symmetric key and can decrypt the data that's in the rest of the file. With OpenPGP format, it works very similarly. The data is going to be protected by a random number with OpenPGP, but then that data key can be encrypted either using a passphrase-based encryption or an OpenPGP certificate, again, a public-private key pair. So the random number to be generated, the data will be encrypted using the random number. That data key will itself be encrypted either using a key that's derived from the passphrase or the public key from a certificate. Now, the OpenPGP format can either use X.509 or OpenPGP certificates, but be aware that OpenPGP certificates do support something called a web of trust, where people get together and kind of say, I trust this certificate. And if enough people trust it, then you might want to trust it too. The encryption facility for ZOS does not support that web of trust implementation, although it can use OpenPGP certificates. So let's go to slide 5 and talk about kind of the implications of some of those options on the hardware that you require. So with Z format data, you can encrypt using clear key encryption, either triple DES or AES. So one of the parameters you would specify as input to the job would be clear TDES or clear AES. And that tells the encryption facility, use the CPAC-F hardware, either the triple DES or the AES algorithm. Alternatively, you can use encrypt TDES, and that says I want to use secure key triple DES. Now, the encryption facility in the Z format was implemented before AES secure key was implemented, so the product does not support secure key AES encryption. If you have a requirement, you might want to submit that to IBM as a requirement to see if you can get the product updated, but the current implementation does not support secure key AES. Now, if you use the passphrase option, if you remember that hashing is done on the CPAC-F, so the encryption facility is going to need access to the CPAC-F hardware to do that. And in fact, the encryption facility presumes that ICSF is going to be available. It is using the ICSF API, so that's kind of a prereq too. If you want to use the RSA option, that's again using public-private key encryption to encrypt your data key. And to do that, you have to have a Crypto Express card available to perform those operations. If you're using OpenPGP, that is implemented using, it's a Java-based implementation. So the hardware requirement depends on how you configure your environment and specifically your security provider. And we're going to talk about Java and security providers a little bit more later on. But if you specify a JCE security provider, that is saying that you don't have any hardware support available. So OpenPGP will use Java software routines to perform the operations that need to be performed, whether it's doing the triple DES encryption, the AES encryption, or doing the RSA operations. It's going to be done in software, and it's not going to use the hardware. Alternatively, you can provide a JCE CCA security provider to the encryption facility in the OpenPGP, and that says, okay, I do have hardware technology available. That security provider will route that work to the Crypto Express cards. Now, even if you're doing clear key encryption and you're not using the RSA option, you still have to have a Crypto Express card available for the JCE CCA support. So even if you're not using the Crypto Express card, you still got to have it to support the JCE CCA. And we'll touch again a little bit more on those providers when we talk about Java in a couple minutes. Let's go to slide 6. Um, so kind of to wrap things up, here's some reference material that's available. The encryption facility is a great way to share data with your partner securely. And I would even suggest that even if you're using System SSL, the encryption facility might have a role to play even in that environment. Now, if you remember, if you're using System SSL, the data will be encrypted as it's put on the communications link between the two parties. The problem is at the receiving end, that data will be decrypted automatically as it comes off the communications link. So, if you do, let's say you're doing an FTP and you're FTPing data to your partner, their automated system on the other end may receive that data and put it into a temporary data set somewhere, but that data is going to be in the clear because it's going to be decrypted as it comes across the communications link. If you don't have the proper security around that temporary data set where it's put until it can be moved somewhere else, it could potentially be exposed. Theoretically, you could use the encryption facility, encrypt the data before you send it to your partner, send it to the partner. When they receive it, it's going to be stored as ciphertext, and they're going to have to take an overt action on the other end to process that data and decrypt it, and hopefully at the same time put it into the right environment where it will have the appropriate security for whatever data is in that data set. So the encryption facility does have a role to play, even though we'll talk a little bit later on about encrypting tape, encrypting DASD. The encryption facility does provide some valuable benefits for protecting data while it's moving between partners. So let's go to the next consumer on slide 7. PKI services. PKI services is a component of ZOS. And so it comes with ZOS, and whether you're using it or not, you have this installed and available on your ZOS system. And what PKI Services does is it gives you the capability to manage your certificates throughout their life cycle. It's a CA, it's a certificate authority for managing certificates that your end users can take advantage of. We're going to see in a minute that it's web-based, so a user can come in and request a certificate up there in the right-hand corner of the circle and say, I need this certificate to protect data, on my workstation or on my distributed system or wherever. The PKI can be implemented so that those are approved automatically, or maybe they require an administrator to approve them. So you might have an environment where, if somebody requests kind of a standard certificate, a 1024 or 2048 bit key with a 1-year life, that might automatically be approved and sent through the system. Alternatively, if they ask for maybe a 512-bit certificate, which is not very strong, you could route that to a real person to say, somebody's got to approve this before we're going to do it. Or maybe if they ask for a really strong key, a 4096-bit key with a 5-year cycle, maybe that goes to an administrator to review and, is this really what we want to give them? So you can automate or make the process manual, and you can customize it to your environment. Once it gets approved, the certificate authority will go through the process of generating the public-private keys that will need to be used by the certificate. It will build the certificate, create the certificate, and then make it available to the end user. So once again, the end user comes back in via their browser, they capture the certificate, download it to their workstation or their distributed system or wherever it needs to be, and then can install it and start using it. In addition, the PKI has some management capabilities. It'll create a database of all of the certificates that's created with expiration dates. So when a certificate is coming up for expiration, maybe you set in your environment, you set a trigger that says when a certificate's within 1 month of needing to be renewed of expiring, you can generate an email that gets sent to the original user, the original requester, to say, hey, your certificate is going to expire in 1 month. Here's what you need to do to renew it. And maybe you could set up the system so that if they don't do anything and 2 weeks before it expires, now you generate an email and send it both to the end user and the end user's manager. So you can raise some flags and say that this certificate's going to expire. You need to do something about it. It can help you prevent certificates getting expired or being expired, and maybe taking down critical applications. Once that user responds and says, all right, let's renew the certificate, now you drive through the process again where the certificate will get generated, get pushed back out, be available to the end user for download and installation. On slide 8, there's a rather busy chart that talks about all of the components of the PKI services. Again, it's a web-based environment, so it can use either ZOS HTTP server or WAS as that front end. It works closely with RACF, so it's going to invoke all the RACDcert commands and everything that needs to be done. There's a whole bunch of scripts and programs that are defined. Now, those are all written for RACF because that's the IBM security solution. But you can certainly modify those to talk to either a top secret or an ACF2. So it will issue the appropriate commands for whatever security server you're running. Now, over on the right, again, it works with RACF. RACF, in turn, can you optionally use ICSF, and it can use ICSF as the key store for those public-private keys that are going to be packaged into the certificates. So if you have ICSF up and running, you can configure the environment to store those keys in the most secure place available in the PKDS and the TKDS. It is not required, but PKI services can leverage it, can take advantage of that protection if it's available. So PKI services, if you didn't know that you have a CA available, most customers I run into, they've implemented PKI off on a Windows or Microsoft workstation somewhere, and they're running perfectly happy. But just be aware that this facility is available. It came with your ZOS, so there's no additional charge. It's just the customization that you would need to do and the configuration and setup if you want to move your company over to using your ZOS system as your certificate authority. So let's go to slide 9, which has some of the reference material that's available for PKI services. That red book is probably a good place to get started with understanding how PKI services works. Let's go to slide. Java. So Java, as we talked a little bit about with the encryption facility and OpenPGP, Java environments can take advantage of the crypto infrastructure. Now, Java relies on a security provider, so there's a configuration file that you define that has the providers that are available in that environment. So you can point to a provider like the IBM JCE provider, which is just a Java implementation of some crypto capabilities. It can do encryption and decryption using AES and triple DES, but it does not leverage the hardware. Alternatively, if you specify IBM JCE CCA, that security provider understands the crypto hardware that's available and the ICSF capabilities, and will actually, instead of performing the encryption operations in their own software routines, it will actually invoke the appropriate APIs and send the work to the crypto hardware that's available. Now, as I mentioned with the encryption facility, if you specify the IBM JCE CCA, you're telling your Java provider, I've got hardware, use it. By golly, you better have the hardware if you specified that security provider. Now, down there at the bottom, the IBM JCE hybrid, that's a more recent implementation. And what it does is it's smart enough to go out and look and say, hey, is there hardware available today? And if so, he'll route work to the hardware. If there's not hardware available, then it'll route work to those appropriate software routines. So the work will get done. So the bottom line is, when you're setting up your Java environment, you've got to tell him what security capabilities are available in that Java environment, and then it will use those as appropriate. A couple others on there. There's the JSSE and the JSSE2. Those are more focused on SSL and TLS implementations. So it provides the APIs to use SSL and TLS. You also have a FIPS capability down there. You have access to the FIPS approved crypto operations. So if you've got to meet FIPS requirements, then you might want to use one of those. And then there's the PKCS 11 implementation. So if you're focused on doing PKCS 11 API calls, you would use that provider to service those calls. On 11, in a Java environment, there's a couple different key store types. The JKS is, kind of the default one. That's the Java key store. That's a flat file that's storing keys in a flat file, protected by passwords. The JCEKS is IBM's implementation of the Sun Java key store. So again, it's using a flat file. It's not using the crypto hardware technology, but putting that key material into a flat file. RACF, JCE RACF KS says put the keys or use the RACF database as the key store. The JCE CCA says use ICSF's key store, specifically the PKDS, to store that key material. And then the last one there is the JCE CCA RACF key store. That says use both of them. Let RACF manage the certificate information. Let ICSF manage the keys. So you'll have that master key protecting the private key that's stored in your PKDS. So you can get the most strength, but you also have RACF to help you manage the environment. And we'll see some of those again later when we talk about tape and DASD encryption. So on 7 or 12 is some key material or some documentation for the Java environments, so you can help you understand those a little bit better. Let's go to slide 13. Secure electronic delivery is not something that you would typically think of when you start thinking about encryption and protecting the data. But back in 2012, IBM announced in announcement letter 212086 that they were going to start sending software that was delivered over the internet. They were going to send it securely, and they were going to start doing encryption and a lot more in terms of hashing and providing some integrity for the packages that you were going to be receiving across the open internet. And there were two problems that developed when they made this announcement. The first one was that the documentation that they provided was not very good. They set up a website so you could test and make sure that you were your configuration was such that you could connect with them and receive this data securely, but it was very difficult. There were a couple customers that were able to test successfully, but a number of customers had problems, and problems were open with IBM and trying to get things resolved. The second issue that developed was that, in fact, a lot of customers have corporate guidelines that prohibit the use of FTPS. So those customers weren't going to be able to receive this data securely and using the technology that IBM was proposing. So as all of this developed, IBM kind of backed off the deadline of when they were going to start implementing this. However, in July of this year, of 2014, there was another announcement, announcement letter 214-311, which basically said, okay, we're going to give you another option. You can use FTPS or you can use HTTPS. And the bottom line is that you can configure your network configuration such that you will be able to connect to IBM and receive those packages using the encryption technology that IBM's in the process of implementing. So that's something you're going to have to start doing in the future. It doesn't to support this, you don't have to have ICSF. You don't have to have the crypto infrastructure. If you don't, then things are going to be done, in software and all. But if you do have the technology and if you do have ICSF up and running, then it's going to provide some benefit in terms of being able to get those products to you securely and with integrity. Now, in addition to that, you're probably already aware that when you do an SMPE receive order, so when you're doing SMPE processing to receive stuff off the network, there is some integrity provided. SMPE is already today doing some hashing, kind of like what we talked about with System SSL. When you send a message, they'll perform a hash on the block or the message and send that with the data so that when you receive the message, you can calculate the hash as well and compare it to the value that was sent. And if they're equal, then you know that the data was sent, that the data that you received is the same as the data that was sent. So SMPE is already doing that today. And if you have ICSF up and running, and if you have the CPACF hardware available, then SMPE will use the ICSF API, the one-way hash API, to perform that hash operation on the CPACF, so you'll get really good performance. And that's all happening under the covers if ICSF and the CPACF is available. Now, if one or the other is not available, then SMPE does have Java routines that will do that hashing for you. Now, that's not going to be quite as fast. The reality is you probably don't care. You're not doing that many receives, and if it doesn't get instantaneous execution, if it takes a couple extra cycles to perform that hash check, you probably don't really care. But you should at least be aware that that SMPE is performing those hashes for you. And if you have the technology available, that's just another component that could be adding a little bit of workload to your environment. So let's flip over to slide 14. Are some references so there's some references there to the announcement letters that announce the FTPS support and the HTTPS support. There's also the driver system software requirements that documents or the planning for installation manuals that document what you need on your driver system. Now, I mentioned that the documentation that IBM put out for FTPS was not very good. So back last year, I was working with some people to try and make that documentation better. And one of the guys was a guy named, I think it's Jorg Stoltz. And that last link down there is attributed to him, but that's not an IBM website. I found this via Google, and that looks like some documentation on how to set up the environment. I'm kind of assuming this might become official documentation at some point, but take advantage of it. It's out on the web. You can Google it yourself, or you can just go to that link and find some documentation. So that might help make the process a little bit easier. So we're going to go to slide 15, and I'm going to take a drink. So I want to talk again about tape and DASD encryption. We talked about this a little bit last month when we talked about database encryption, but I want to come back and revisit it, just make sure everybody's aware of it. And really the focus here is the fact that when you're doing tape or DASD encryption, you can use ICSF and the PKDS as your key store for that. So the way that tape and DASD encryption work, let's talk about tape first. When you install an encrypting tape drive, one of the first things it does is it kind of registers itself with the ISKLM. So let me back up. If you order encrypting tape or encrypting DASD from IBM, then you must install this product called the IBM Security Key Lifecycle Manager for ZOS. And before that, it was called SKLM, and before that, it was called TKLM, and before that, it was called EKM. This is the most current implementation of it. It's a software product that kind of acts as a communication system between the drive, whether it's tape or DASD, and a key repository somewhere. So again, when you install a tape drive, one of the first things it does is it registers itself with ISKLM. It says, "Hi, I'm a new tape drive, and my address is 1234, and here's a public key that is associated with me." So when you want to write encrypted data on that tape, so sometime later you're going to come along and you're going to mount a tape and you're going to write some data on it, and you want it to be encrypted, that tape drive is going to tap ISKLM on the shoulder and say, "Hey, remember me, tape 1234? I need a key so I can encrypt this data." What ISKLM will do is it will go out to a key store somewhere and say, "Hey, we need a data key to encrypt some data, and here's the public key of the tape drive." So what the key store is going to do is it's going to generate a random number that'll be the data key, and the key store is going to encrypt that data key under the public key associated with the tape drive. So that ciphertext is going to be handed back to ISKLM. ISKLM is going to hand it to the tape drive. The tape drive has the corresponding private key, so now he can decrypt that data key and now use that data key to encrypt the data. Now, the challenge comes with, okay, how are we going to decrypt that data later on? So the other thing that happens when you create an encrypted tape is you provide a second public key that's associated with the user that's going to read that data later. Whether it's your partner or whether it's you internally, you're going to provide a public key, and when the tape wants to create that original data key, it's not only going to get the key encrypted under the tape drive's public key, but it's going to pass a key label for the end user that's going to decrypt it. So your key store in that case is actually going to create two versions of the data key. One's going to be encrypted under the public key of the tape drive. It's also going to provide a second copy. The same data key is going to be encrypted under the reader's public key. So the key store is going to hand both of those back to ISKLM. ISKLM is going to hand both of them to the tape drive. The tape drive is going to use the one that's encrypted under its public key to recover the key. And it's going to take the second one and just put it on the tape. And it's going to put it on the tape, physical tape itself, and it's going to put it in the memory, the random access memory or ROM memory that's on the physical drive. So when the reader mounts that tape, they're going to pull that encrypted copy off the tape. They're going to point to the private key that's associated with the public key that they gave you. Now they can decrypt the data key, and now going to using the same process that ISKLM, it's going to hand that ciphertext key to ISKLM. ISKLM is going to hand that ciphertext and the label of the key, the associated private key. So now that's going to get handed back to the tape drive so the end user can read the data as well. Encrypting DASD works similarly. The difference is you're only going to have the device key there because that DASD volume is never going to leave your environment, or if it does, when it does, the keys are no longer going to be available. So the only key that's used in the DASD environment is the public-private key associated with the DASD volume itself. Same thing. When you install the DASD the first time, it says, hey, I'm device ABCD. Here's my public key. Make a note of it. When it comes time to encrypt data on that DASD, the DASD will say to ISKLM, hey, I need a symmetric key to encrypt this data. ISKLM is going to tap the key store on the shoulder and say, hey, I need a random number and encrypt it under this public key that's associated with the DASD device. That ciphertext gets handed back to the DASD device. The DASD device will use the private key that's associated with the public key. Now he can encrypt the data using that DASD. So ISKLM is simply a kind of a traffic cop routing requests from the physical device to the key store, whatever it might be. The key store is actually responsible for generating the random numbers and protecting them with the appropriate public-private keys that are needed. So let's go to slide 6. And down there at the bottom, the 4 key stores that we saw before, you can use any one of those 4 key stores with ISKLM. So you can just have a Java implementation somewhere using a Java key store in the JCEKS. Or you can use only ICSF as your key store. So if you specify a provider of JCECCAKS, then ICSF will store the key material in the PKDS, and ICSF will take care of generating the random numbers and protecting them under the appropriate public-private keys. If you use JCE RACFKS, then RACF is your key store, and RACF will generate the random numbers and will encrypt the data under the public keys as appropriate. And then finally, again, if you have JCECCA RACFKS, then you're using both RACF to manage the certificates and ICSF to provide the CCA security of your key material. So ISKLM is just kind of a traffic router that can use ICSF and the crypto hardware if you configure it that way. Slide 17, some reference material. That red paper is actually kind of concise and short. It's, I think a little bit less than 50 pages. It can probably help you get started with understanding how to implement ISKLM. On slide 18, we have the IBM Ported Tools. Now, that's a separate product that you can get from IBM to provide SSH support. It provides secure encryption for remote login and file transfers and some open SSH functionality. The original implementation of the IBM Ported Tools did not extensively leverage the crypto infrastructure. In fact, the only time it used the crypto infrastructure was to do random number generation on the Crypto Express cards if it was available. Now, it turns out that OpenSSH does a lot of random number generation, and this can help your performance. But when it comes to actually performing encryption, symmetric key encryption or hashing, the Ported Tools, the original implementation, was not leveraging the crypto technology that was available. A couple years back, IBM put out APAR OA 37278, which in fact did allow the ported tools to at least do triple DES and AES encryption, get that work routed to the CPACF hardware, and it could also do your MAC verifies and your MAC generate some of the hashing technology was now able to use the CPACF hardware as well. You do have to be running on at least HCR 7770, but that's been out a couple years, so you should probably be good there. Now, there are other competing products out there. There are other vendors that have ported tools software that you could install instead of IBM's. My understanding is that at least some of those have been able to use the IBM crypto infrastructure for some time now. So they could do it even before the IBM ported tools were enabled to use the technology. Let's go to slide 19. This is simply the reference material for the IBM Ported Tools product. So let's go to slide 20. Uh, the Enterprise Key Management Foundation. A couple years ago, IBM made a big announcement about this thing called EKMF, the Enterprise Key Management Foundation. And really, the focus there was that first bullet was centralized key management solution. What they were really pushing was the ability to manage key material, and that certainly is worth doing, worth looking at. I think key management is a critical component that you have to have, and EKMF can help with that. EKMF and this key management solution, which is actually called DKMS, or is supported out of the IBM Crypto Competency Center in Denmark. And they also have a couple other offerings, ACSP, EKMP, CAT, and the PCI hardware collection. These are just marketing packages that IBM was selling. So I want to focus on that ACSP, the Advanced Crypto Service Provider, because what it does is it gives you the ability for your remote systems, your distributed systems, to use the crypto technology that's available on z/OS. So let's go to slide 21. EKMP ACSP is a client server solution that gives you the ability to execute crypto workloads from your distributed system, but the work's actually going to get done up on your system Z. So there's software that you're going to install on the distributed system. There's software that's going to be installed on the server itself. And when the distributed system needs a crypto function performed, that work will actually get routed across the network securely. The work will be done on System Z using that infrastructure, and then the results hand it back to the distributed system. So this provides some advantage, a number of advantages. First of all, you don't have to have crypto technology, crypto hardware on every one of your distributed systems. They can each just send the work back to the host, and you can leverage hopefully the crypto hardware, the CPAC-F and the Crypto Express cards that are already installed on your host system. And if you're not driving those to capacity today, that's a good use for that hardware just to get some more work over and take advantage of that resource that's available. It also provides some advantages in terms of key management. The key material that the crypto operations are going to need are going to be stored and managed by ICSF up on the host system. So you don't have to worry about installing keys and distributing keys out to each of these distributed systems. Now, the distributed systems are still going to have to know which key label to reference or to use, and that's going to be passed along with the work that needs to be done on the host. But the actual security and integrity of the key material is going to be handled by ICSF and the hardware technology that's up there. And as we talked about back early in the year when we talked about the Crypto Express hardware and then about ICSF, it does provide a tremendous amount of security and integrity for your key material. And then because it's managed up there, that's also going to simplify your DR process, because ICSF and dumping those key stores to tape and taking them to your DR site, that's already provided by ICSF. You're already doing that for your host system. You don't have to worry about the DR for the distributed system, the keys that are used on the distributed systems. Let's go to slide 22 and look a little bit more at how it works. As I already mentioned, there's ACSP client code that will get installed on the distributed system. There's server code that'll be installed up on the host system. And that that distributed system, there's a number of different platforms that are supported. Basically, any kind of Java-based system can invoke the APIs that this ACSP product provides. So your application is going to invoke those APIs, and those APIs can either be CCA, the Common Cryptographic Architecture that's traditionally been implemented on System Z, or the PKCS11 technology is now available in this ACSP client as well. So you can invoke either of those APIs. That client software is going to take that request and it's going to say, oh, okay, that needs to be routed up to the host system to be performed, and it's basically just going to be configured to use send it to a particular IP address, so that crypto request or that function request is going to get shipped securely across the network. The servers on the server side, the ACSP server code is going to receive that and basically translate that into the appropriate ICSF API that will then get routed to the appropriate hardware on the server system. When the hardware is done, provides the results back to the server is going to turn around and send those results back again across that secure network to the ACSP client on the distributed system, and then hand the results back to the application to do whatever it needs to do. Now, that being a system Z bigot and even a ZOS bigot, I want to tell you that that server system is going to be running ZOS and ICSF, but in reality, you could actually install that server code on an AIX system or on a Linux system, maybe running on X, or you can even install it on Pure systems. So there's lots of flexibility in terms of who can service those requests for you. So neat technology that can give your distributed systems, it can help your distributed systems so you don't have to manage and maintain crypto hardware on each and every one, but you can turn around and leverage the capacity and the infrastructure that you have available up on your server. So let's go to slide 23. Slide 23, some reference information. Down there at the bottom, the announcement info. That Z Solutions is a website with lots of Z security solutions, and there's a link down on that page to that marketing flyer down there. Again, these products were developed at the Denmark Crypto Competency Center. Those guys are really knowledgeable in the crypto environment. Let's go to slide 24. And we're going to shift gears for the last 15 minutes here or so and talk about things that you should be doing now. And we kind of touched on all of these throughout the year. I just want to come back and highlight these four that if you're not doing them now, you probably should be. And first of all is going to be rotating your keys. If you're subject to PCI, the PCI requirements say that you got to change your keys periodically. Now, let's start with the master keys. Whether you're doing that yearly, bi-yearly, every 5 years, depending on whatever local regulations you might be subject to, you should have a documented process for changing your master keys, and you ought to be doing that, whatever that process or whatever your corporate guidelines say. But the bottom line is you should have guidelines and you should have a process and you should be executing it. When we talked about the DR environment, we talked about the fact that, if you're going to an outside provider like a SunGard or an IBM, when you finish your DR exercise, that's probably a good time to change your master keys, is when you come back. And so you ought to have that documented process and be executing it. We haven't talked a lot about changing application keys, but the PCI requirements change it, and I would suggest this is just as, if not more important than changing your master keys. You ought to be changing your application keys. Now, if you're a systems guy, maybe that's not your responsibility, but your application folks should be doing this. They should know how to change the keys. If you're using a product like the encryption facility for DB2 and IMS, the process for changing them is basically unloading and reloading the tables and changing the edit proc in between. So it's fairly straightforward to do. Might, take some time for the unload and the reload, but you ought to be doing that. If you've got applications that are invoking APIs and using keys that are stored in the key stores, those ought to be changed periodically. Whatever is right for your environment. Kind of the bottom line here is, if there's a compromise, if there's an exposure, or if a critical resource leaves, maybe a key manager leaves the environment, you probably want to have a process that says, we ought to change the keys shortly after that event so that if there's ever any issue, if there's ever any question, you say, well, it couldn't have been them. They could not have gotten in because we changed the keys afterwards. It just makes sense to be able to go to your CEO or the judge if it gets that far and say, hey, we did our due diligence. We changed the keys at the appropriate time to protect ourselves. If they got in, we at least tried to do what was right. With public and private keys and certificates, that process is a little bit more automated by the expiration and renewal of certificates, and it's a little bit easier. But you should be changing those periodically, whether it's every 1 year or every 2 years. You should be changing keys just to be able to say we're doing the right things, we're performing the right crypto hygiene to keep ourselves clean. On slide 24. The second thing you should be doing is securing your crypto resources. In a couple different places this year, we talked about the fact that you should protect your key stores, your CKDS, PKDS, and TKDS using RACF. ICSF is the only address space that needs access to those key stores. So nobody should have read access. Yes, maybe a fire call ID, and there's a couple cases where somebody might need to look at a key or look at the key store, but those should be logged. The logging should be turned on, and it should be greatly restricted, and it should be audited. Who's looking at those key stores and why. Similarly, you should be protecting your keys. And I would suggest that not only production keys, but even test keys. We've had some customers who kind of opened their test environment up, let just anybody create key material. And what happened was people would go create keys and then forget how they used them or where they used them. And there was a fear that maybe they had protected production data. And if they got rid of those keys now, maybe there was some data out there that might need to be decrypted next year or at year end as part of the business cycle. So there was some concern there that, hey, we just let anybody do it and we created keys all over the place and now we don't know what those keys are used for. We don't know if they're protecting anything important. So I would suggest having a process for defining keys and limiting who has access to those keys. Similarly, you should protect the APIs. That provides some separation of duties. That is, the people that are authorized to encrypt and decrypt data should probably not have authority to create and delete keys, and vice versa. The people that have authority to delete and create keys shouldn't have access to use the other APIs. It just provides some separation so that you can say, hey, they could not have downloaded this data and re-encrypted it under another key because they couldn't create the key to do that. So it just provides some more protection so you can stand up to your management and say, hey, we're doing the right things to protect this data and make sure that it's secure. On slide 26, when we talked about performance, we talked about the fact that there's not a lot of performance data. The metrics are not very good for doing capacity planning and that sort of thing. That said, you probably ought to be saving these records so you have them. So you can go back and look at trends and maybe look at how crypto utilization is going hopefully up over time and not down. The CPU measurement facility, that gives you the ability to look at your utilization on the general purpose engines and how much crypto work is being done. You probably don't care today, but 6 months from now, if your CPU is, maybe you're reaching maybe it's time to upgrade and you're trying to figure out how much crypto workload's going on. If you've been capturing those 113s, maybe you can go back and look at the trends and see what those counters look like in terms of how many AES operations are doing, how many triple DES operations, how many hashing operations. Just capture the data. Even if you don't need it right away, have that history so you can go back and post-process it maybe later and understand what's going on in your environment. And then finally, on slide 27, this one's a little bit fuzzier in terms of what you need to do, but you really should keep your ear to the ground and understand who's using your crypto. For things like CICS transactions and connections and DB2 connections or between DB2 subsystems using SSL, just know that that's going on. Know that you're protecting that data. The other issue you have here is you can have what I call stealth users in crypto. You can have people that are using the CPACF instructions, the native instructions, the KM instructions to encrypt data or to perform hashes, and you really aren't going to know who they are. It really takes some digging to figure that out. So keep your ear to the ground. Know what your application developers are doing. Do they know about the KM instructions? Are they implementing them? If you know what's going on in your environment, when it comes time to start looking for problems, maybe you can start with some of those guys. Hey, you were telling me that you were using the KM instruction. How often are you doing that? How much work are you doing there? Just so you know, try to get an idea of what kind of work, what kind of crypto work is being performed in the system. It's hard to tell, I will admit that, but just pay attention to your users and keep an ear out to what they're doing. So with that, I'm going to wrap things up here. It's been a fun year. As Jerry has mentioned, we are going to continue these in the new year. Not sure exactly what the schedule is going to be. We're probably going to start off with some of the basic stuff again, the intro and the hardware. Crypto is one of those things that you probably need to hear it multiple times before it sinks in. Kind of a funny story. I had a customer who she came to share fairly regularly, and every time I did an intro to crypto session, she sat in on it. I mean, like 4 or 5 times straight, she was there. And at one point, she came up to me and said, I'm getting a third or I'm getting 3/4 of the way through the session before you're losing me. And that's just the way crypto is. There's so many acronyms and buzzwords that you got to hear stuff a couple times. So we're probably going to start off with repeating some of those introductory sessions again, and we'll probably repeat some of the other sessions, and hopefully we'll add some other sessions as we go along. So with that, I'm going to turn things back over to Jerry, and we'll open it up for questions.